So let's start chapter 2. The chapter 2 the main focus of chapter 2 is to discuss the four paradoxes which arises because of the two conflicting postulates of quantum mechanics. The first is Schrödinger equation, which gives us deterministic evolution of wave function. So once we are given psi at a particular time, we can use this equation to calculate psi at later times. And the second postulate is state vector reduction. The Schrödinger equation doesn't tell what value of we will get when we will do an observation. It will just tell us by Born interpretation we can say what are the different probabilities of getting the result. So in state vector reduction, the wave function collapses to a particular eigenfunction of the observable. So the second point is state vector reduction. Now the first paradox which is von Neumann infinite chain. So in this thought experiment, we will abolish state vector reduction and we'll go just applying the Schrödinger linear superposition of Schrödinger equation, which means that given a set of solutions of Schrödinger equation, we can take linear combination of them, and they will still satisfy the Schrödinger equation. So using this idea, we will show that we won't be able to get any observation. So the thought experiment is like this. So we have a quantum system as a Q. I think S is used in this book, and we have an measuring device M. So in usual quantum mechanics, in usual discussion, we say that M is a macroscopic object, so it follows the laws of classical physics. But here the point is we will take S and M both to be quantum system, and because both are quantum system, we will have to use Schrödinger equation to tell the result. Now if we are doing an observation, and corresponding to that observation we have an observable. Now that observable is represented by a linear operator in Hilbert space. Now if this wave function of the system S is not an eigenfunction of T, then it will be linear superposition of the eigenfunctions of T. So this starts the chain. Let's say that the wave function in S is not an eigenfunction of T, rather it's a linear combination of those eigenfunctions. Now when it will interact with M, if we don't have a state vector reduction, so what we will get is linear combination of those interactions. So we will have a bigger psi, which will be linear combination of these interactions. And if we add another measuring device to get result, we will get more linear superpositions. So in this way, if we are going to add more and more, we won't be going to get any result. Now this is the point of this infinite chain. So to get result, we have to introduce the state vector reduction. This is the point of this idea. Now the second paradox is Schrödinger cat. Now Now we will use the ideas of previous thought experiment, and we will arrive at more paradoxical situation. Now the idea starts with this. The usual, there's a cat placed in a box and we have a radioactive substance, and there's a probability 50% chance it will decay within an hour, or it won't decay. If it decays, we have such a system that the cat will die. We have arranged a mechanical arrangement. We have a mechanical arrangement that if the radioactive substance decays, if a single atom of radioactive substance decays, the cat will die. So how are we going to use the ideas of previous experiment in this case? So the starting point is the decaying of atom. Now the wave function of the atom is, it has 50% chance it will decay, and it has 50% chance it won't decay. Now once we are going to arrange lot of relays and mechanical system, once they will interact, by the ideas of previous experiment, they will form a chain of the linear superposition of wave function, which gets bigger, and in the end what we'll get, if the particle decays, the cat will die, and if the particle doesn't decay, the cat won't die. So we will get this. Now because of this, if the deterministic evolution of the Schrodinger equation is not broken at some intermediate point of this chain, we will get this situation. Now what is paradoxical about this case is that we know in macroscopic world we have definite answers. It's not that there can be something which is dead and which can be alive. So this implies that the state vector direction happens at some intermediate point of the chain. The third experiment is Wigner's friend. In this experiment, and this third experiment, we have the case of previous one, but now we add another feature to it, which is we are going to put an observer inside the box, and there's another person outside. So the person inside the box does observation of quantum system, and this box or room is closed, and the outside person doesn't know the wave function, but once the person inside does the observation and knows the definite result. For example, let's say he is doing the experiment, Stern-Gerlach experiment, and he finds out that the particular electron has a spin plus h bar by 2. So unless the person outside comes inside and sees the result, he doesn't know the result. He doesn't know the spin of the electron. So this adds another. So this adds the issue that whether the state vector is contextual. The fourth is Einstein's negative interaction. So in this experiment, So in this thought experiment, so we have an object which radiates a particle at a single time, and the radiation is given by spherical wave. So you have an object, I will use a different page. You have an object and it radiates particle in spherical wave, and you arrange detectors as this. And these are arranged as such that once the particle is emitted, they are going to observe. What I mean is, we are going to get the observation whether it gets detected by D1 or D2. Now, if it so happens, there are two cases. One is when it's detected by D1, it won't be detected by D2. And the second case is, and the D2 is placed in the spatial region quite far away from D1. So the particle will be detected by D1 first. Now, as the particle, if it's not detected by D1, it will be detected by D2. But if we see this experiment in as follow, that if the D1 is having no interaction with the wave function, the spherical expanding wave, but even when it is not interacting with the spherical wave, we are getting a collapse of the wave function. By collapse I mean it is reducing into the wave function which is an eigenstate of D2. So this is the idea, that without an interaction we are still getting some state vector reduction. Now, going along this line, we have a fifth one, which talks about known locality, but I don't know whether it is useful for chapter 4. That's why, if if it is useful, I will discuss it there. Otherwise, I will leave it for now.